Hey everybody, welcome to the first section on Unit 3. So as you probably know by this point, this whole unit is more in depth about the periodic table, and we'll also talk a little bit more about subatomic particles. But of course, let's talk about the periodic table first. This image is a relatively recent periodic table, and you can tell it's pretty recent because we have these elements that are listed here. Now, it's not entirely updated only because I have some of these placeholder names. So these actually have real names and symbols already. So they're Oganesson, Tennessine, which is named after Tennessee because there's a really big research laboratory in Tennessee. Nihonium and Moscovium. And Moscovium, I think, is after Moscow in Russia. So this is a pretty good periodic table. And I like this one also because it's color coded. So of course you have your alkali metals here in group 1, except for hydrogen, it's kind of all on its own. Your alkaline earth metals, you have your transition metals, lanthanides and actinides down at the bottom, your halogens, your noble gases, and then these are your metalloids in the light blue. This particular periodic table calls them semi-metals, and that's basically the same exact thing. So the periodic table isn't just put together this way to make everybody's lives miserable in high school chemistry. Every element has its own home based on a very specific reason. And this all comes down to who discovered this, which is Dmitry Mendeleev back in the 1800s back in Russia. So there's a picture of Dmitry Mendeleev, and he was the first one who organized the periodic table, and he organized it by increasing atomic mass. And when he did that, he noticed similarities in these elements as he would start to organize them. So some of the elements would start to group together, and he would find that they would have similar properties as atomic mass increased. So, which hopefully you started to see in that dry lab we did the other day. But elements with similar properties happen to fall kind of next to one another on the periodic table. So he was able to take each of the elements, basically write a card for them, and treat them like puzzle pieces and put the puzzle of the periodic table together. And he organized it that way, which is really, really neat. And this is what his first periodic table happened to look like. You know, he was Russian. So as you could see, this is all written in Russian up here. And this was his first periodic table that was published back in 1869. And you'll notice that it's not too different from our periodic table. I mean, clearly it doesn't look the same, but there's also a lot of similarities. So what I want you to do is I just want you to pause this video, and I want you to fill in that Venn diagram, or start to fill in that Venn diagram. And we're going to go over that in class the next time I see you. So what are some similarities between Dmitry Mendeleev's periodic table, this one right here, and our modern periodic table? What are some similarities and what are some differences between each of them? So again, pause this video and just take a second to fill out that Venn diagram, and we're going to go over that together in class the next time I see you. Once you're done with that, you can restart this video. Hopefully you noticed that in Dmitry Mendeleev's periodic table, there were some question marks. And let's go back here. So there happens to be 2 question marks in particular right around here. And I also have a question mark here and a couple more down here as well. One of the coolest things about Mendeleev's discovery of the periodic table, or that he was able to put this puzzle together, is that based on their location, he was able to predict the existence of elements that weren't even discovered yet, which is so cool that he was able to do that. He was putting these pieces of the puzzle together and said, well, I know something has to go here based on how I'm organizing this periodic table, but I don't know what it is yet, but something has to go there. So he put a question mark and an approximate atomic mass for that. And he almost dead on predicted the properties of some of these elements. So what he called this element right here, number 68, was Eka aluminum. And that's basically just the element that's next to or below on our periodic table, below aluminum. So based on its location, he said, okay, well, I know that this element has to have an atomic mass of about 68 atomic mass units. I know that it has to bond to oxygen in this ratio. I have to have some element, whatever this element is, it's simple. It's going to bond in a 2-to-3 ratio. Its density should be about 5.9. It's going to have a low melting point and it's going to have a high boiling point. A few years later, gallium was discovered, and gallium fit in that piece of the puzzle. And if you look at the real physical properties of gallium, they're almost dead on to what it would be. So this part of chemistry, this, putting this periodic table together was a really, really great advancement for the time. That we were able to predict the existence of elements that weren't even discovered yet. And it's based on their location on the periodic table, which again, really, really awesome. That's one of the biggest contributions that Dmitri Mendeleev was able to do with his first organization of the elements. We now know, however, if you look at a periodic table, it's not actually organized by atomic mass. And that's where this man, Henry Moseley, came into play. And he was a physicist. And you're going to find that a lot of chemistry discoveries kind of were physicists in a way, because in order to really understand chemistry, you have to know how chemistry works and why it works the way that it does. And physics helps to describe chemistry, which is why a lot of physicists are credited with these discoveries. So Henry Moseley discovered that it was atomic number, not necessarily the mass, that was the basis of organization on the periodic table. So if we look at a real periodic table, this one's actually updated all the way. We can see those new elements. Down below here, these are your atomic masses. And we now see these numbers, and that right there is the atomic number. That's what Henry Moseley discovered is actually a much better way to organize the periodic table. And a better way to say the atomic number more so is the nuclear charge. That means how many protons are in the nucleus. You'll see that it's not a very good indicator. Atomic mass isn't a very good indicator because there's actually a couple of anomalies. And one that I can point out to you very easily, I know that there's more than just this, but this is one that I know. If you look at tellurium and iodine, tellurium actually has a little bit of a higher atomic mass than iodine, which is why atomic mass really isn't the best way to organize the periodic table. Henry Moseley discovered it was in fact the atomic number. And that gives us the periodic table that we have today. And this is a tabular arrangement of the elements in rows and columns, or periods and groups, highlighting the repetition of properties of the elements. So we started to talk about it in Unit 2. All of your elements in Group 1 are alkali metals. Well, your alkali metals are very reactive with water. They're so soft they can be cut with a knife. They're not very dense. They all have a metallic luster. So all of these elements, even though they're not right next to each other on the periodic table, as I go across a group, when atomic number is increasing, the properties repeat themselves. So it goes through this whole entire trend of some properties, and it comes back to an alkali metal. And then that whole trend repeats going across to a noble gas, which is not reactive. And then it goes back to an alkali metal, and the whole trend reacts until it gets back to a noble gas. And then it goes back to an alkali metal. That's what periodic means. It's a repeating pattern over and over and over again in order of atomic number, an increasing atomic number. Let's take a look at some of the most important piece of information you'll find in the periodic table. So here's just a very general little block that you would see. And there's some things that you need to be very familiar with. This top number right here, always the whole number, is your atomic number. And we'll talk more about what the atomic number is in a little bit. Of course, you have the symbol for the element. It is very important to know the symbol. It makes, knowing the symbol makes it very easy to identify those elements when you're doing reactions and things like that. You don't want to have to look at a periodic table constantly to see what element it is. You should start to just recognize them. This number down here is your atomic weight. It's also your atomic mass. It's your molar mass. Chemists like to have like 18 names for the same thing. I don't know why. It's just the mass of that element. It's not the whole number, the one with all of the decimals. Notice this number here actually has 6 significant figures. So we know the molar masses or the atomic weights of these elements very, very well. We have the technology now to measure these out to 6 significant figures. And then of course, you'll also have the name of the element. This periodic table does not have the name, which is why, again, it's very important to know the symbols for them. Not for all of the elements. I don't know every single one, to be honest, but I do know most of them. Let's talk about what atomic number is. So the atomic number, there is a meaning to that. Henry Moseley discovered that the periodic table fits much better by atomic number. That's not just an arbitrary number that was assigned to each element, but really your atomic number is the number of protons that you find in the nucleus in each atom of that element. So for example, hydrogen has an atomic number of 1. That means that every hydrogen atom has 1 proton in its nucleus. That's what makes hydrogen hydrogen, the fact that it has 1 proton in the nucleus. Helium has 2 protons in its nucleus. That's what makes helium helium. And we could see here that right in the center, so this is an atom, very common representation that you've probably seen in lots of your other science classes. In the center is our nucleus, and that's where our protons are housed. So here's our blue ones right here. Actually, if you were to identify this element based on this picture, you could in fact do that. So let's count the number of protons in the nucleus. 1, 2, 3, 4, 5, 6. So if we were to say, what element would this be? What element has an atomic number of 6? Hopefully, if you look at a periodic table, you could say that that would be a carbon atom. There's also some neutrons in there, which we're going to get into in a second. But what I want you to do now is try sample problem 1. So tell me, what's the atomic number for each of these elements? Pause this video, take a minute or 2, and just answer those questions. Hopefully you found that beryllium has an atomic number of 4. So that means every beryllium atom has 4 protons in its nucleus. Fluorine, 9 protons in its nucleus. That's its atomic number. Iron has, I wrote them down here because I don't know atomic numbers off the top of my head. Iron has 26 protons in its nucleus. Krypton has 36. Silver has 47, and lead actually has 82. And again, you can just easily identify those by finding where it's located in the periodic table. So for example, here's lead. Lead has an atomic number of 82, and it has an atomic mass or an atomic weight of 207.2. Let's also talk about the regions of the atom. So kind of going off of this right here. Of course, we just talked about protons, and protons are what are housed in the nucleus of an atom. And the nucleus contains your protons and neutrons. So neutrons are another type of particle that actually have no charge. They have a mass that's very similar to the proton, but they have no charge. And your nucleus is very, very small in comparison to the rest of the atom. So if I go back at this picture here, notice that the nucleus is relatively small compared to the rest of all of this open space right here. So your nucleus is a very small, dense region at the center. You have those protons and neutrons that are packed really, really tightly with one another. And this is actually where most of the mass of an atom originates. And that's because your protons and neutrons are significantly larger than your electrons. So your nucleus is in the center, that is your protons and neutrons. And then around that, you have these electron clouds. And your electron clouds, of course, are comprised of electrons. And the electrons exist in the clouds. Think of them like birds in the sky. And I know birds don't fly in the clouds, but we're just going to pretend. So you have these massive clouds in the sky, and they just take up space, right? And they're just like that with atoms too. These electron clouds take up a lot of space. And the birds are always flying through the clouds, or the planes. You can even see the planes are always flying through the clouds. That's how electrons are. The electrons themselves are very small in comparison to the actual clouds themselves. They just fly around the clouds, just like birds would or planes would in the sky. And your electron clouds are what surrounds the nucleus. So your nucleus is in the very center, and your electron clouds are around that. And although your nucleus is where most of the mass of an atom comes from, your electron clouds is where most of the volume comes from. So like we said, the nucleus is very, very dense in comparison to the rest of the atom. So if I look back here, here's my nucleus, very, very tightly packed. Particles are not that much bigger in this picture, but these particles are bigger in real life. And here's our clouds. Notice that most of this is actually empty space. And my electrons live in these clouds that are surrounding that nucleus. And the electrons themselves are very small in that whole entire cloud. Now, this is a very basic representation. These clouds are actually in 3D. They have all these different shapes. So we don't get into that, however. So if we were to compare the masses of these subatomic particles, so here's a proton, here's a neutron, and here's an electron. We might do a lab with this actually, but rather than using these exact masses, it gets very annoying to have to remember all of these numbers. Plus, if somebody said to me, oh, a proton weighs 1.6 or 1.672 times 10 to the negative 27 kilograms, I wouldn't know what that means. I mean, what is that relative to this pencil, right? It really doesn't mean anything to me. And a lot of chemists, in fact. So what they did was they said, okay, well, what are these masses relative to one another? And if you look at these numbers for the protons and neutrons, they're actually almost the same. So they differ out to that fourth significant figure, to that thousandths place. So we say that protons and neutrons actually have the same exact mass, really. And even though they're not identical, they're pretty close to one another. And if we were to compare the electron to that, the electron doesn't weigh anything in comparison to the proton and the neutron. Think about something really, really heavy, like if you have a sumo wrestler, and you have, a baby right next to the sumo wrestler, and you're comparing the weights of them. The baby doesn't weigh anything in comparison to the sumo wrestler because the sumo wrestler is so large. And that's kind of how we categorize these as well. So protons and neutrons are so big and they're so heavy, the electrons really don't contribute anything to the mass of the atom. Let's go ahead and just fill these in quick. So we call protons, neutrons, and electrons, they're all called subatomic particles. So subatomic, below the atomic level, and they're just different particles. Proton, again, hopefully we do a little activity with relative mass, but the relative mass of a proton is about 1 atomic mass unit. Again, we're not going to use those very specific numbers. We really don't care about those. We just want to know relatively what's their mass. The neutron is about the same. So that also has a relative mass of 1 atomic mass unit. And like we said, the electron doesn't weigh anything in comparison because it's very, very small. Charge. Protons have a positive charge. Neutrons have a neutral charge. And electrons have a negative charge. And symbols. I usually like to put the symbols here just because I use them a lot in worksheets and just in general throughout class, especially the electron. The proton is symbolized by a lowercase p with a plus sign. The neutron is a lowercase n with a little notch, like a 0, basically. And the electron is a lowercase e with a little dash. I use this one all of the time, especially this electron right here, as do lots of textbooks and other chemistry teachers and YouTube videos and all that. Well, we call all of those subatomic particles. Here again is a very basic representation. So we'll see our protons and neutrons in the center, and then I have this big electron cloud. So notice that most of an atom is in fact empty space. There's nothing here. But these electrons just exist in these electron clouds, and they don't have to stay on the perimeter, on the circumference. These guys are just somewhere in here at some point in time. They just kind of exist in the clouds, like we said. Normally, it's kind of an inaccurate way to represent atoms. It's really not 100% correct to say that they just exist on this perimeter and whiz around that way. They just exist in here. If we were to identify what element this is, you can count the protons. 1, 2. This would be the element helium. This is a very basic representation. So again, the nucleus is very dense in the center. The particles are very big. This is where most of the mass comes from, but most of the volume comes from these big electron clouds, not the electrons themselves. Here is a more accurate representation. You don't have to know this, but I just like to show it. So, because this is technically not very correct. Here's your nucleus again, very dense in the center. And our electron clouds have different shapes to them. So this right here would be the first electron cloud. We have our second electron cloud. We have some other electron clouds in the second row or in the second period. We have our third electron cloud. So there's a lot of stuff going on here. You don't have to know all of this, not right now, but I just like to show it in case you're interested as to what an atom actually looks like. For now, this more than suffices. That's where we're going to stop for today. If you have any questions, make a little note in your notes. Let me know. Ask me in class. And otherwise, I will see you guys very soon. Bye.